Konnichiwa from Thailand. Good afternoon, I am Supanon Jamon Surya, Master Degree student in the School of Chemistry, Suratnari University of Technology. Today I'll present my work in the topic of computer simulation of the topological effect on crystallization of linear and cyclic polyethylene. This presentation will include the introduction about the polymer with different chain topology, with comparison between the cyclic and linear polyethylene, and the polymer crystallization. Then, the technique of Monte Carlo simulation of the polymer is introduced, followed by the result, discussion, and summary. The objective of this work to have better understanding at the molecular level for the effect of chain topology on the crystallization behavior of polyethylene melt by computer simulation techniques. Polymer crystallization is very interesting and important in polymer science and technology. We can view the polymer crystal in various length scales starting from the smallest dimension as the unit cell, where each polymer chain has to packed together and has the folded crystal structure proposed by Andrew Keller in 1957. As the polymer varies to be perfect, there should be the amorphous portion sandwiched between the crystalline unit as a layer of structure. Then this unit assembled to the spherulite, which is large enough to observe by the optical microscope. The cyclic polymer have been synthesized in the laboratory scale recently, and it brings about many interesting properties due to the lack of chain end, in particular for the folded chain structure in the polymer crystal. The cyclic chain should behave differently. Interestingly, the crystal growth rate is faster than the linear chain as observed from the experiment. It is very interesting to study the future for the crystallization characteristic of the cyclic and linear polymer, because the cyclic polymer is very hard to prepare and no commercial samples are available. So we want to study this polymer using the computer simulation technique. We perform the coarse-grained simulation instead of using the atomistic model, which consumes too much computational time, maybe months or years, to simulate the polymer crystallization. The method we start from the map the polyethylene to the coarse-grained on-chain structure to the lattice, and then perform the Monte Carlo simulation to investigate the polymer crystallization based on the various calculated properties. This is the overview process for the polymer simulation procedure used in this work. First, we modify the parameter for the coarse-grained polymer chain mapped into the second nearest neighbor diamond lattice or 2NND from the RIS model. Then we use the Lennard-Jones potential function to determine the intermolecular non-bond interaction, and we use the Metropolis criteria to determine the movement of polymer on the lattice. The rotational isomeric state or RIS model was proposed by Paul J. Forey, was applied to define the single chain conformation of polyethylene. This is the statistical weight matrix for the polyethylene with the column and row represent for the trans gauge plus gauge minus conformation, with this energy as the sigma and omega for the polyethylene. For the first order interaction, we determine from the repulsive group by Newman projection, with the first two bonds, which is gauge plus and gauge minus, will be defined as sigma due to the closeness of the repulsive group and the one for trans state. Then the second order interaction for the further bond will mostly repulsive with a different gauge state, defined as omega. Other state will be defined as 1 because a CH group is far away from each other. Each coarse-grained bit contains one ethylene unit or two carbon backbone, and then we map them into the second nearest neighbor diamond lattice, which is derived from the diamond lattice as raised dot We remove the blue dot to get the distorted cubic lattice, which is the coordination number is 12, which is higher compared to the conventional cubic lattice. The polymer simulation on the 2NND lattice will allow the faster speed of computation and less memory usage compared to the other simulation method. After we mapped the polymer into the second nearest neighbor diamond lattice, we can classify each conformation to 4 types from their length scale, from the bit I to I plus 2 as A, B, C, D group, which can be defined as 4x4 matrix. As the polyethylene had a symmetrical torsional energy profile, we can further group the C and D state together so that we can reduce them to 3x3 matrix. After we define the single chain parameter, we use the Lennard-Jones potential 12.6 for interchain interaction. The method is based on the treatment of real gas using the second Vao coefficient for the interaction between two bits in the lattice. In this work, we use the first 3 shells of discretized Lennard-Jones potential energy to speed up the calculation. After we define the Hamiltonian to describe the energetics on the system, the metropolis criteria is used to determine the movement of the bit on the lattice. If the total energy is getting lower, that movement will be accepted. But if energy go higher, we have to determine the comparison of Boltzmann factor to the random number lambda. If it is larger, the movement will be accepted. Otherwise, it will be denied. This was performed to prevent the local minimum trapping. First, we present the result of total interchain and intrachain energy of the whole system for the cyclic and linear polyethylene. This is the conventional way to validate whether the system is equilibrated or not. As we see the early state of the simulation, the energy becomes stable very quickly. In ordinary case, we will presume that the system is equilibrated, but not for the polymer crystallization system. So we have to perform the other techniques. Then we use the orientational autocorrelation function. It is seen that the cyclic chain relaxes very fast, while the linear chain is slower because it's form almost trans conformation. Then we use the mean square displacement of the center of mass to see the movement of translational mode. The linear system diffuse larger, so we can confident to justify that our system are equilibrated using these 2 criteria. The simulation was performed by stepwise cooling of both systems from the melt state at 473 Kelvin and equilibrate each step for 15 million Monte Carlo steps until it reached the room temperature, and we perform total 200 million Monte Carlo steps for equilibration of the crystallization process. This is the equilibrated coarse-grained structure of the cyclic and linear polyethylene. Comparison between the melted state and crystalline state. You can see both systems are folded beautifully into the crystal structure with more orderly structure on the linear system. The crystal formation process is affected by the transfaction, which increased to the value about 0.85, which the 1.0 is completely crystallized, but due to the long chain of polymer, there will be some gauge conformation to allow the polymer folding. For the cyclic, we will have the lower value due to the more gauge conformation of the ring topology. Then we see the anisotropic chain in the polymer chain dimension in terms of the radius of gyration in each laboratory axis. During the crystallization, the cyclic chain elongate preferably in the one particular direction to the z-axis to be the cylinder-shaped like, while the linear system is mostly elongated to the y-axis and expand into x direction than z direction in film-like shape. Now we investigate the overall bond orientation in the system using the global order parameter calculated from all bonds. The linear chain achieved SG value about 0.9, which is substantially larger than those cyclic chains, the SG value equal to 0.5. This result suggested that the linear chain can form crystal with more ordered structure compared to the cyclic topology. The lower SG value of the ring system might be the effect of more lap folding for the ring double layer in the crystal structure. Then we determine how bond at a different distance of the shell number will be oriented using the order parameter. As the crystallization proceeds, the order parameter is monotonically increased. It is also seen that the bond at the second shell show the highest correlation as the parallel orientation. The order parameter at the higher shell is steadily decreased, suggested more random orientation for the bonds stay far apart. Next, we investigate the order correlation function in the same chain. In general, when the crystallization takes place, the decay of the order parameter is slower as the chain adopts more trans conformation. The cyclic polymer has two upturn points due to the double folding of the ring polymer to form the crystal structure. Next, we determine how the bond conformation as the number of consecutive bonds in trans state. At the melted state, the pattern value of the both cyclic and linear system almost indistinguishable. Compare between two temperatures. The polymer at the room temperature can have longer trans sequence as expected. When the crystallization proceeds, compare between these two topologies at the crystallized state. The linear chain have trans sequence up to the 27 bond, while the cyclic polymer can go up to around only 24 bonds. We analyze to compare the chain packing between linear and cyclic chain using the pair correlation function. In the melted state, the pair correlation function of two systems are almost the same, while at the crystallized state, there's significant difference in the linear chain packed denser than the cyclic. As the linear chain have chain ends, it is easier for the linear chain to find position to stay closer to themselves while the cyclic chain cannot. To get some properties that are related to the real experiment, we calculate the scattering factor using this equation. Simply speaking, we find the distance of Rij between all bit pair and multiply by Q, which is the scattering vector. We sum this quantity for the all bit pair and normalize by square number of the bit to get the SQ value. The plot at the left is different of the SQ, which at the time origin to signify the crystal formation. The peak intensity will increase as the crystallization proceeds. On the right side, we compare this quantity between the linear and cyclic polymer. It is seen that the linear crystallize better than the cyclic. Note that the amplitude of the cyclic system can be up and down, meaning that the crystal may be not so stable or it changes orientation, while there is steadily increase for the linear chain. This is the summary for this work. I would like to thank the SUT University for molecular simulation using the high performance computer cluster and DPST scholarship for funding the tuition fee for me and the research fee. Thank you for your kind attention. Please feel free to ask the question. Thank you.